Okay, good morning, afternoon, or night, or whatever, man. Good. What's up, everyone? This will be. Oh my God, look at me. This will be my finals for the deep learning course from Bio. Basically, the course final is to implement deep learning, specifically the NNs, the neural networks, and I think one of the rubrics is to emphasize more on CNN, specifically image processing. So that's what I'm doing, kind of. So let me explain to you. So basically, my project is in relating to the thesis, sort of both kind of vibration and sound analysis. This is more towards sound analysis of industrial machines. I don't exactly know if this is manufacturing machine, but this says pump, so it should be manufacturing. But it's basically analysis of sound, specifically spectrograms, to find out whether or not a machine is in a normal condition or abnormal condition. In the industry, there's something called back to normal conditions, which means to replace everything and going back to the machine's normal condition. And because of that, have chosen this dataset. It's called the Mimi Pump Sound dataset. There are multiple versions of this dataset. The original one, which is around 34 gigabytes, consists of four machines. I think there's pump fans and two others, divided into normal and abnormal. But because it is so large, I decided to use only one to basically restrict just the scope of this experiment. I'm using the pump sound dataset, which in total is around 948 megabytes or 1.33 gigabytes in this case. These are all sound files, specifically in format of WAV. And if you're a musician, you probably know. But this is the abnormal. Let me close it. This is normal 138 plus 381. It's kind of a lot of files. Each file is about 2 to 3 megabytes a piece, only a couple of seconds long. And so basically, how this relates to CNN is the spectrogram. So basically, changing, as you can see here, sound-based predictive maintenance, a small experiment using CNN to analyze and predict maintenance based on spectrograms derived from recorded machine sounds. So, sorry about that. So let us start here. If you can't see it, I think there should be a bit more. Should be enough. So this is all the dependencies and libraries: OS, Kekel Hub, Torch. But I want to emphasize on Labrosa. Labrosa is a sound processing library which we'll be using to change the pump sound into spectrograms. Uh, Scanlearn, Lib for the graphs, whatever. Verify T4 GPU, I'm using T4 provided by Colab here. Just downloading the data set, as you can see here. And now, data preprocessing and MEL spectrogram feature extraction. So again, as I said before, we'll be using Labrosa to both load and change it into spectrograms, which is done here. X feature, Y labels, whatever. This is only to extract it. And then it turns it into a spectrogram. So this is an example of the spectrogram. So you can see right here, intensity, the labels are temporal windows. I think this is time, intensity profile, or the dynamics. And the next is to split the train. This is actually for train validation. I'll be using the test later on. I'll show you, but as you can see right here, it's not a lot of files, but it has a workaround. So total training 270, total validation 68. And then defining the 2D, specifically CNN architecture, right here. Scroll it, whatever. It's fine. Kernel size, cool. And then the model training itself, I use 15 epochs, so 15. I thought it was enough because it's such a small sample size. There's losses. And then the performance charts, let me back that up here. Okay, execution epoch pass. this is all formalities. And then of course the accuracy score itself, as you can see, it's going well. Again, because the sample size is so small, but I think it's good enough. Um, the accuracy is absolutely crazy. 0.94, what? Okay, that's whatever. And this is the accuracy for both abnormal and normal operations. Cool. And then this is the real-time testing, which I just grab a file from from here. The dataset itself. I'm just run it. Boop. Oh jeez, I've already run it. Boom. So I think, yeah, this is abnormal. And abnormal fault detected, 99.67% AI confidence. If I change it to normal and run it, AI confidence 68.04%. Wow, it's actually pretty close, but yeah. So it does actually work, and it's pretty cool. And so how this relates to my thesis is basically like this. I hope you can see it, but so this is my current architecture. Ooh, excuse me. For my thesis. So the machine has a sensor. It's mainly going to be speed. So the HMI, the WainTech CMT20 AC HMI, or the data logger basically, will track the machine's speed, gives it to the edge node, which will be a Raspberry or a Jetson, and then process it through ANFIS, or I think it's I forget what it's called, neural network fuzzy inference system, I forgot what it's called. But it's basically a neural network plus a fuzzy. And the output of that will be used to control a Siemens PLC. And then PLC will control the machine, the speed of the machine. Now, reports from operators in the field have suggested that there are actually sound and vibration indicators of whether or not a machine is supposed to be maintained or supposed to be in maintenance or is broken. So what I'm suggesting is sound analysis and vibration analysis, which has been implemented in other spaces or in other manufacturing enterprises. So what I'm suggesting is an acoustic mic to the machine itself running 24/7. It will chop it up on the edge node. It will be processed through this model. This model is pretty small, so it should be able to be run by a Raspberry Pi with an NPU, or a neural processing unit, a hat for the Raspberry Pi, or I think Jetson has another one. And then that can also dictate the Siemens PLC in conjunction to the speed analysis from the WainTech HMI. This has a lot of novelty because sound analysis and vibration analysis specifically implemented in Indonesia's manufacturing space has not been used a lot. So what I'm thinking of here is, instead of maybe adding jobs to the field operators because they have to be able to have time to maintain other stuff besides internal parts and spare parts, this setup, and specifically this CNN model, which has been tested with the Mimi pump sound dataset, can be used to detect whether or not something needs to be maintained, a spare part needs to be maintained. And that maybe in the dissertation, that will be sort of the main point, is like adding more parameters, because the sound for a broken bearing, for a broken shaft, and other parts of the machine are different. So if I can find a larger data set with more parameters, then it would just completely negate the usage of scheduled maintenance and more towards predictive maintenance by using sound and vibration analysis. So that is all for my finals. All the resources will be in the description below. You can look at the collab. You could edit it all you want, but everything will be in the description below. Thank you so much. That is my finals, and I'm uploading another video probably tonight. So I'll see you then. Peace.